Hello everybody. We're going to have a look at another application of integration in this video, and specifically we're going to look at the areas between curves. Now this is different from what we've looked at in the last video where we looked at areas of regions, but it was always the region basically between a curve and the x-axis. In other words, just the y value relative to where y equals 0, and between two limits of x. X is a and x is b. This one is different, where we're going to look at the area of a region between two separate curves. Okay, it's the same idea, and you'll get the idea very quickly as I show you. Now this one here, for example, we're going to find the area of the region bounded by the parabola y equals x squared, that's this little baby here, and the line y equals 2x. Okay, that's that one there. So this is a different kettle of fish, you see. We're dealing with this yellow bit in here, right? The area between two curves, not a curve and the x-axis, chosen over two x limits. Okay, so let's have a look at this. First we need the points of intersection before we can do our integral with a lower x terminal and an upper x terminal in our integral. We need to work out what these points of intersection are between these two curves. So we just do some simultaneous equations here like we're very used to doing by now, and let's do that. Okay, looks like it's a pretty easy one, doesn't it? Okay, we got that. Take out the x, I think. Yes, and therefore we've got x is 0 or x equals 2. Well, that fits in very nicely, doesn't it? So let's have a look over here now. Okay, now this is what we're doing. This is x is 0. This is x is 2. Okay, now again, I implore you to think of areas of rectangles. Okay, areas of rectangles. That's what makes up any integral. So we've got to work out whether we've got a positive signed height or a negative signed height, and also similarly whether we've got a positive signed width or a negative signed width, because that's going to determine, when you multiply the signed height by the signed width, whether your integral is going to be plus or minus, because for an area we need it to be plus. We can't have a negative area, so you've got to sort of do a little bit of smoke and mirrors on your integral to make it come out positive so it coincides with an area. So now, having said all that, it looks, if I go from 0 over to 2, if I start from 0 and I end up at 2 in terms of my x, then I'll be going in the positive x direction. If you think of that as a directed line segment, I would be going from a lower value to a higher value, which gets me high minus low is a positive answer for my widths, right? That's positive. Now in terms of the heights, okay, if I put my integral such that I'm saying the higher value, which would be this red curve, which is y is 2x, minus the lower value, okay, which in this case is y equals x squared, then higher minus lower gets me a positive result. So if I frame the integral in that way, where I'm saying this y minus this y, then I get a positive directed line segment in the y sense, don't I? Yes, so therefore that's positive as well. So therefore I can ensure now from doing that little bit of analysis that my integral is going to come out positive, and therefore I can quote that as my area, right? So now you see the way I've framed this. The integral is 2x minus x squared. High minus low gets me a positive y, and going from low to high in the x sense gets me a positive width. So everything's good, and I can work this out confident in the knowledge that I'm going to get the area. Yes, that's what I was just saying. Yes, positive width, positive height gets me a positive value, and let's go for it since the area. So therefore the area, yes, equals the integral, which equals that. Now all we've got to do is basically work it out, guys, and that's just straight anti-differentiation throughout the nation, which we've been used to doing. I think that looks right, doesn't it? And evaluated from 0 to 2 as a definite integral, and we'll get that once you work it out. I think that's right. Yes, because the lower terminal gets us absolutely nothing, right? So that's 2 squared minus 2 cubed over 3, and that'll be 4 over 3. And that's my area, okay? That's my area. It's also my integral, but they're both the same. But I want to go to great pains to show you how to do this, because I want you to get it right. Because in the exam, they'll give you all kind of abstract stuff here, where you've got to be able to think about which one's positive, which one's negative, because they give you five multiple choice answers where they've just switched everything all over the place, and they're switching the terminal, the order of the terminals. There all kinds of things they're doing there. They're putting negative integrals in, and you've got to basically have your wits about you to know what's what in terms of what an area is, yeah? And it all depends on whether the integrals are plus or minus. Okay, having said all that, what do we got here? We have to calculate the area of the region enclosed between the curves with equations y equals x squared plus 1, which looks like this one, and 4 minus x squared, or minus x squared plus 4, which is the yellow one, and the lines x equals 1 and x equals minus 1. Okay, so it's just in here, from here to here, this yellow segment here. Alright, now we've got to work out the area again. So we have to make sure we've got a positive integral, guys. So we use the same procedure. This time we don't have to work out the points of intersection because we're not using those. We're just going from x minus 1 to x is plus 1. Now there's my little integral. So look, you know the drill by now. If I go from there over to there, from minus 1 to plus 1, I'll get a positive width. And if I do upper minus lower in terms of the y, the height, I will get a positive height, and that's what I'm going to want. That's what I want to do to get the positive integral which coincides with the area. Okay, so that's what we're doing. That's plus, and plus a Rooney, and that's what we get. So the integral. So I did the upper one, which was the 4 minus x squared, minus the lower one, which was x squared plus 1, integrated with respect to x from minus 1, from the lower value of x up to the upper value of x, ensuring that I'm going in a positive width sense, positive height sense here, everything's good. So I get this kind of thing here, positive width, positive height, positive result, everything's positive. So therefore the area is going to be, now I've just worked all that out, I've just got rid of those brackets, 4 minus 1 is 3, minus x, yes, minus x squared gets you minus 2x squared, so everything's good. And now we just integrate here between these limits and we'll have our answer, okay? So what do you get for the integral? Come on, do it in your head quick before I reveal it. Yes, 3x minus 2/3 of x cubed, evaluated between minus 1 and plus 1. And what do you get there? Oh, goodness. Yes, good. That looks like it's that. Very good, which will be 3 sixes are 18 minus 4, which will be 14 over 3. Yes, now, by the way, look, if you're probably sitting there, or some of you will be sitting there thinking, yes, okay. You know, if you really wanted to be, see how this, when I looked at that, I thought, oh, that's so interesting. That's just this thing. Again, really, right? It's doubling this thing here, which makes complete sense because this whole thing's symmetrical about the y-axis anyway. So if you just wanted to really, if you just chose to evaluate it from 0 to 1 and then double your answer, you'd get the right answer, and you'd be very clever for thinking of that, yeah? And which comes with practice. You know, you get to think of these things when you do more practice, because practice makes perfect, as they say. And it's true. Right, another one. Now we're on a roll. Good gracious, look at this. Now this is a little you've got to be careful with this little beastie. Look, this curve's on top on the left-hand side of the y-axis, but it's underneath on the right-hand side of the x-axis. So this is one where we've got to be careful. Because, guys, I can tell you right now, if you evaluated the integral from this point here, which looks like minus 1, we better check up on that though, and plus 1, guess what you'd get? Guess what you'd get? If you did that on your CAS handheld, you'd get a great big fat 0. Now, I want you to think, why would that be? Why would that be? Why would it be? Well, I'll explain in a moment, okay? Now, let's do it. Okay, we need the points of intersection, yes, as I was saying. So we've got x cubed and we've got x, yes, for the, which is the x, the red one, yeah? Y equals x, or g of x equals x, yeah? So we've got to do the points of intersection, therefore x cubed equals x, and therefore doing all that, taking out x, the common factor. Oh, look at that. That's a difference of 2 squares. Are you aware of the difference of 2 squared? Yes, you are. So there. And we'll evaluate that and we'll get x equals 0 or x is plus or minus 1, which all looks like it makes perfect sense. As I was saying before, that looked like plus and minus 1, or minus and plus 1, and therefore we're feeling very confident about that. Yes, now, what have I said there? Goodness. Yeah, now, this is this big NB, which I was looking at before. For the area, we need 2 separate integrals because the curves change their height order on either side of the y-axis. That is, on the left-hand side of the y-axis, x cubed is higher, but on the right-hand side of the y-axis, x is higher. So therefore, look, this is what's going to happen, guys. If you just went x cubed minus x, right? X cubed minus x. On this side of on the left-hand side of the y-axis, x cubed minus x, that would be positive, yes, wouldn't it? X cubed would be higher, minus x, which is lower, so you get a positive. Upper minus lower gets you a positive height. But over here, x cubed minus x is negative, yes, so the integrals come out to be negative, so long as you're integrating in the same direction of x, which I'm assuming we're going to go from minus 1 to plus 1. Yes, so this side, if you do x cubed minus x, yes, positive, but if you do it on this side, you get negative, so the integrals would then cancel out the positive here with the negative there, and you'd get a result of 0. Why don't you go off and tootle off and do that on your CAS handheld when we finish this video, and amaze and shock yourself. That's because that's what's going to happen, I can tell you. Right, so we'll do them as 2 separate integrals. Yeah, that's plus, yes. On this side, if we do that way, same direction, that's plus, and then that one will also be plus, but that'll be only if you go red minus blue would be plus, yeah? So that's what we've got to do. So the area would be, now, you notice the way I've done it, from minus 1 to 0 of blue minus red, right? Plus 1 to 0 of red minus blue. That ensures that I get a positive integral over this side, over the right-hand side of the y-axis. Do you see that? So important, isn't it? So important. Yes. So therefore, what have we got all here? This is very, very interesting. This is a similar case to the last one we did, you know. Very similar case, because I've got basically this is the same as, or is it? Is the same as, I think it is, yes, it'll just be double. Yes, it is, because of the way these terminals are set up here. Yes, this is going to get us the same as that. So you evaluate it like that, or if you liked, bearing in mind the symmetry of the situation here, it is all symmetrical, or at least what I mean is this area is identical to this area here, right? So you could, if you liked, you could just go blue minus red from minus 1 to 0 and then double it. Yeah, you could just do that if you wanted to. Save yourself a little bit of calculation, headaches and all that. If you're in an exam, that'd be a good one to note, yeah? It'd be a good one to note. It'd save you a bit of trouble evaluating something sort of twice, as it were. Anyway, I've done it there for you, the long way, and it's all looking pretty okay. And what do we get? Yeah, see, look, there you go. That's what I said before. This is exactly the same as this. Yes? So it works out to be a half, a quarter each. This is a quarter, that's a quarter. Okay, so the area is a half. How do you like that? Yes, maths is beautiful, I know, it is beautiful. Now what do we got to do now? We're on a roll, truly on a roll. So what's the area of the shaded region of the graph? Well, that's a pretty gurky looking thing, isn't it, don't you think? I suppose we've got to work out the terminals here, this one and this one, I would think. One of them's cos, which one's cos, the blue one's cos, and the red one's sine. Okay. Look, do you know what I always do, guys and gals? What I always do, just to make sure that I'm doing the right thing here, is I draw a rectangle in, and I always make sure that the top one remains the top one, hitting the top of the rectangle, and the bottom one remains the bottom one, hitting the bottom of the rectangle. Because sometimes, in some of these things, if you look at them, you can't do it that way. And if the top or the bottom changes midway or part of the way through your X span over which you're integrating this thing, you have to do it as two separate integrals, because your rectangles have to have the same top and the same bottom within the same integrand, if you know what I mean. Yes, so that does qualify in this case, although it confused me when I first looked at it. I thought, heavens, is there something changing places here? You've got a bulge there, and you've got a bulge down here, and goodness knows, we've got to work out the lay of the land here before we go rushing in where angels fear to tread, or like a bull in a china shop. So, everything's good. I think it's red minus blue, don't you? Red minus blue from this one to this one will get us plus everything. Positive widths and positive heights, I think. So we better work out those POIs before we do anything else, yeah? POI. So, okay, we need to know where cos equals sine, don't we? Well, I know the answer to that, but I'll show you. Yes, we better do a simultaneous equation throughout the nation. And what do we do? Yes, that's you divide both sides by cos for those situations. You probably know that from methods. And we need to know that this is between naught and, yes, between naught and 2 pi, don't we? Probably between, yes, that's right. We have to go from naught to 2 pi. There will be two of them between naught and 2 pi. So if you don't restrict the domain, particularly if you were doing this on the calculator, you get the calculator gives you a general solution which just sends you around the twist, trying to work out what it's talking about. So I always like to sort of restrict the domain in my head when I'm doing these. I'm not going to use the calculator, I'm just going to use our heads, but I thought I'd give you that little warning anyway. So tan x equals 1, why don't we just get a cast diagram out and have a look at that. Tan x equals 1, well that's easy. The basic angle is pi and 4, and we're dealing with quadrant 1 and quadrant 3, so those two quadrants, so therefore that angle there in there has to be pi and 4, so we're dealing with pi on 4 and pi plus pi on 4, which would be 5 pi on 4, wouldn't it? Yes, that's great. Oh, look, isn't that terrific? We worked it out. We worked it out. Alright, so now we've got our POIs. Now we've got to integrate the thing now. There's my rectangle, okay? So I'm going positive width, positive height, if I do the red minus the blue, that is, y values, and everything will be good. So, regarding the integral, what I'm saying here is sine x is at the top of the rectangle, cos x is at the bottom of the rectangle throughout my x span over which I have to integrate, so everything's alright, and everything will work out. Yes, sine x is there, cos x is there, so it's going to be sine minus cos, guys. In order to have positive integral equals area, we go sine minus cos. From pi on 4 to 5 pi on 4, and that's very easy to do now. Very, very easy to do. That's going to be minus cos, remember, because cos gives minus sine as a derivative. Therefore, if you've got plus sine, it must have been minus cos, which gave rise to that as the derivative. Remember, we're anti-differentiating here, right? Now, so, therefore, we get that. Yes, sine gives cos as a derivative, so if you've got minus cos, it would have been minus sine in here, giving rise to that as its derivative. And we're evaluating between pi and 4 and 5 pi and 4, so let's just quickly do that. We get all that stuff, and we get all that stuff, and what do we get as a result? Oh yes, 4 over root 2. 4 over root 2 is the same as 2 root 2. So that's the area of that yellow section there, okay? How are you going? Are you getting it? If you look at rectangles and the signed widths and the signed heights, everything will be good. If you don't do that, well, I don't know what's going to happen. So it's better to do that, and you won't go wrong. What's this one here? Oh, that's a pretty strange looking beast, isn't it? It's the area of the shaded region. We've got y equals cos x is the blue one, and y equals sine 2x is the red one. So this one's got half the period of this one. That's why it's all behaving a bit strangely. So we've got to work out this yellow area in here. So I suppose we better work out, yeah, see, this is another one of these mixed up ones. See, look, blue's on top here and red's on top there. So we've got to do two separate integrals, and we need to know the POI here. We need to know that POI, guys. Be a PI, a private investigator, and work out the POI. So let's go with that. Yes, right, so y equals cos x and y equals sine 2x. Now I think I can feel a double angle formula fighting to get out in my mind here. There it goes, at the POI, we got that. Yes, hello Mr. Double Angle, how are you today? We've got this. Now we can basically sort that beast out. Okay, it'd be pretty hard any other way, but we've done it now. We can take out the common factor of cos, can't we? Yes, very excellent. So cos x equals 0 or sin x equals a half, where x is going from 0 to pi on 2. Indeed it is. Now, if cos x equals 0, therefore x would equal pi on 2, well that's very fortuitous. We've got this POI here, haven't we? Lovely, my oh my. And if sin x equals a half, x would be, within that domain, x would be pi on 6. So this looks like pi on 6, guys. Isn't that marvellous? We've got it, and it makes sense. Okay, now what have I said here? For the area, we need two separate integrals, but yes, because the curves change their height order on either side of the POI, as happened in a previous example. So, look, no problem. We're out of the danger now. We know what we're doing. So, to the left of the POI, cos x is higher. To the right of the POI, sin x is higher. Okay, so it's upper minus lower. That's what I've got to do. This one, cos x is on top, sin x is down here. This one, sin x is on top, cos x is down there. So looking at our situation, we've got a positive width there, a positive height there. So that's providing we do cos minus sin, upper minus lower in terms of the y, and that'll get us a positive integral. There we've got positive x, providing we go from left to right, and we've got, if we do sin 2x minus cos x, upper minus lower, that'll be positive height. Okay, so that's looking good. Now, let's do it. Yeah, cos x, sin x, yes, we get all that. Thank you, Mr. Computer, and here we go. So the area is, okay, cos minus sin 2x on the left-hand side of the POI there, from 0 to pi on 6, plus sin minus cos on the right-hand side of the POI from pi on 6 to pi on 2. And evaluating all that stuff, what do we get? Oh, goodness. Have to be careful. You know, you have to be very careful doing all this stuff. This is where students go wrong. There's a lot of processing going on here, so be jolly careful and don't be an algebra hero. Don't skip any steps, okay? I worked all that very, very carefully before I put that on the screen. Okay, so sine of pi on 6 is a half, plus cos of a half of cos, wait a minute, cos of pi on 3 is a half anyway, so it's a half of a half, minus sine of 0, which is 0, minus a half of cos of 0, and cos of 0 is 1. Strange as it may seem, it's 1. Remember? So a half of 1 is a half. See? You've got to be very, very careful. Similarly, I've got all that stuff over there. Alright? Now, look at all that stuff everywhere. See? You have to be very, very careful. So take it easy. That cancels. And what do we get? We get all that apparently, and therefore the answer looks to be a half, guys. A half. Yes, so there you are. Beautiful result. Beautiful result. And that's the end of the story. So, now, do you know how to do areas between curves? Yes? You do integrals between curves and you make sure the integrals come out positive. If they come out negative, you either reverse the terminals on the integral or you just go negative the integral. Okay? Okay, thank you very much for all that. I hope you're having a wonderful day and we'll see you in the next video. Okay, bye-bye.